Hello, welcome back. Today we're going to be continuing our discussion from yesterday, talking about how do we find the absolute extrema under a surface. So we have to go over a couple of definitions. One, where we're going to be looking at a boundary. And in our boundary for here, we're going to be looking at primarily the xy plane. We typically call the xy plane R2, like so. And that's really what this means. We're just looking at the real numbers, the cap R's is for our real numbers, and two, we're looking at a two-dimensional plane. And what we're going to do is we're going to project this plane up into a surface. And anything within that boundary of that plane, we're going to try to find out where the maximum and where the minimum value occur. So, and we say that the region R2 is called bounded if it is completely contained in a disk. And again, this just comes from our normal understanding of the domain. When we look at the disk, we're looking at the xy plane and anything within a certain region. So we have x goes from some value from like negative a to a, or y can go from negative b to b, and that's why we call it a disk, because we're looking at the domain from the x's and the y perspective. We'll call that a disk. It doesn't have to be a circle, it just has to be bounded, and that's within those bounds of the x and y. And here we have a couple of examples of an open region. Remember, in an open region for x and y, these cannot be included, so there's no endpoints here. And we prefer a closed region, where we can include endpoints in order to find these. So remember, what we're looking for today is, given a surface, how do we find the absolute maximum and minimum values? And this comes from idea from calculus as well. And in calculus BC, or first and second semester calculus, in order to find the extreme value theorem, we called that the EVT last year in calculus. In order to find those values, there's a couple places we have to look for. We have to find our critical numbers. That's where the derivative was 0 or D and E. And two, we had to check our endpoints right here. And what the bounds are looking for is going to give us our endpoint. That's going to be kind of the tricky parts right there. Now, in multi, it is a little bit trickier for us, but the idea is still the same. We got to find our critical numbers, which we talked about yesterday, and today we're going to find out, well, how do we find the endpoints of a surface? So here's the extreme value theorem for multi-dimension, for multivariable. Same thing. If a function is continuous on some interval in our xy plane, in our domain, then there are points D that will give us an absolute and an absolute minimum value. So in other words, as long as we have a continuous function, no holes, no gaps, no jumps like that, we're guaranteed to have an absolute maximum and minimum value. And again, we see this we saw this last year in BC as well. So what the extreme value theorem is really telling us is that every closed and bounded, if a surface is closed and bounded, it has to have an extreme value theorem. And last year in BC, to show this, we used what was called the candidates test. Right there. So, very easy for us to do. So, what we're going to do is, we want to just imagine we're standing on the xy plane. So what we're going to do is we're going to imagine we're standing on the xy plane somewhere on the surface. And we want to look up and down. And we want to find, well, what is the absolute minimum value, or what could be the absolute maximum value on the surface at that point in our domain. So it's like, imagine looking up at clouds, and you want to find out, well, where's the highest point on the cloud? Where's the lowest point on the cloud? That's what we're looking for today. And let's say we only want to be in the state of Colorado, let's say. So let's say you're staying in the state of Colorado, and in all of Colorado, what's the highest mountain, or what's the lowest valley is what we're kind of looking for here today. All right. So in multi, to find the absolute extreme, or to use the candidates test, the EVT, there's things that we have to look for. And this is what the really EVT says. That's all these really say right here is, one, In order to find the extreme value, we have to find where like last year in BC, we have to find where the slope is 0. Like in BC, if I want to find out from A to B, what's the highest value, what's the lowest value, we first have to find those critical numbers, those critical points. This is going to be in our bounds, though, and that's all that says. R2 just says are within our bounds. 2, we have to check the edges. These are like checking the endpoints. I'll give you an example in just a few moments. These are the edges. And what these are the intersection of the surface with the bounds, with the bounds themselves. These are going to be a trace, which we're going to see in just a few moments. And the third thing we have to check for are the corners. And this is where it gets a little bit tougher for us. These are going to be like the endpoints of our surfaces. So to give you an example, let's say we are on the XY plane right here. And we have this surface. So let's see here. Let me see if I can build this out here really good here. So let's say we're talking about a bound on the XY plane like so. And we have this surface on the XY plane. It's above it, it's below it. So what we're looking for, well, down here, these are the bounds. And let's say we have our surface and it kind of looks like this. Goes up, scrolls down, up, and down, something like this. So what we're looking at is we want to check everything within the bounds. And if you notice on the bounds here, we do have this trace right here. The surface is in the middle of our little rectangle there in the XY plane. This is our trace. In other words, this is the edge. The edge is where does our surface intersect the bounds. And these little points right here, where the traces or the edges meet, these are our corners, and we have to check those as well. And what we want to do is we want to check everything within the bounds. We have to check the traces and the corners. So we're going to check all of them, all of those points to find the absolute maximum and minimum. We're going to find the absolute max and mins today. And it's tedious, but it's not too hard to do. So let's go ahead and take a look at an example here. So let's say we're given the following surface, and we're asked to find the absolute minimum and maximum value of our function right here. We're given the following bounds. X is between -1 and 1. Y is between -1. We now know that our R2 is closed, that our bounds is closed right here. So what we're kind of looking at right here, if you think about this, is if we're looking on the XY plane, we're going to be between -1 and 1, between -1 and 1. What we want to do is we want to find within this box right in here, where is the highest and lowest value possible of our function. So the first thing we have to do is we have to find our critical points. So let's see what this graph kind of looks like though first, okay? I got a kind of graph right here. Hopefully it's still kind of going here. There it is. There's the graph right there. Here's what the graph of our function looks like. And if you notice at the origin right there at 0, 0, it goes all the way up to 4. So we now kind of know on the domain -1 to 1 that the lowest point is probably going to be 4 there. But if we look between -1 and 1, we can kind of find out where those higher points are. So we kind of know what this function looks like. What we want to do is mathematically, how can we determine those highest and lowest points? So how do we do that? Well, step 1. We have to find the critical point. And we did this yesterday. To get the critical points, or CPs, we're looking at the interior. This is the inside of our bounds. This is going to give us any bumps low valleys, high mountain peaks inside our bounds, -1 to 1 for the x and -1 to 1 for the y's. To do that, we're using our critical, we're going to use our partials. The partial with respect to x is 2x minus 4xy, and our partial with respect to y is 8y minus 2x squared. Because we're looking for critical points, we do set these equal to 0, like so. And for the first one over here, I'm going to factor out a 2x, and that's going to give me 1 minus 2y. Set that equal to 0. I get x equals 0, y equals 1/2. Now, to get the corresponding values, I have to solve. If I'm going to now plug this in to solve for the corresponding other values. In other words, when x is 0, into this function, we would get 0 equals, well, that's just going to become 8y minus 0, so y is 0. So one of my critical points is going to be 0, 0. We don't know the z value yet. If y is 1/2, we get 0 equals 4 minus 2x squared. Solving this, we would get x equals plus or minus root 2. We don't have to worry about these, the plus or minus root 2, because this is outside of my domain. That is out of the domain, so I don't have to worry about that part, which is nice. All right, so once we find the critical points, now we have to do the hard part. This is a new part. This is very new for us. We have to find the edges. To get the edges, these are the traces where the bounds meet the function. And this is a little bit tougher. So we have to find the traces. So to find the trace, we've done this a long time ago. If one of my bounds is x equals -1, I just plug that into the function itself. Let x equal -1, and I could plug it in. We would get f of -1y. This is equal to, and this becomes just, plug it into the function, 1 plus 4y squared minus 2y plus 4. So we would get the following. We would get 4y squared minus 2y plus 5. Now, remember what I said. What we've created here is if we're looking at the xy plane, in other words, we're holding x constant, so we're only looking at, in this case, really the yz plane. So this would be like the yz plane, and on the yz plane, and remember, x is -1, so this would be a trace at x equals -1. We get a parabola between y is -1 and 1. And what we're looking for is, well, what's the lowest point on that parabola here? So now, if we hold that, if we're looking at this trace here on the yz plane, where x is -1, I just need to find this pointer. Well, from Calculus 1 last year, how do we find that point? Very simple. We just take the derivative and set it equal to 0. And that's what we're going to do here. We would say f prime -1y, the derivative there, becomes 8y minus 2, set that equal to 0. We get y is 1/4. So another possible critical point is -1, 1/4. There's another one. But that's not the only edge. We also have x equals +1. And if x is +1, we would get f1y becomes, and it's, you notice it's going to be kind of the same thing here, 1 plus 4y squared minus 2y, but ran out of room there. Let me restart that over again. That's kind of terrible. Looks terrible there. There we go. We would get f of 1y, and that becomes 1 plus 4y squared minus 2y plus 4. Taking the derivative again, we would get 8y minus 2, set that equal to 0. Again, we get 1/4. So another possibility is 1 and 1/4. Whoops. And we don't know the x value yet. Okay, so we did for x equals 1, x equals -1, but now we got to check the other bounds. Y is -1, y is 1. So for y equals -1, plug in, we would get f of x -1, and that becomes x squared plus 4 plus 2x squared plus 4. Take the derivative, we get 2x hold on here. We get 2x plus 4x equal to 0, and that's just going to give us x equals 0. Sorry about that. So another possibility is 0, comma, -1. Hold on here. Sorry, I'm getting so annoyed with my pen here. And blank space. There we go. And we also have to check y equals 1. Y equals 1, x1, and what are we going to get here? And we would get, again, x squared plus 4, but this time we get minus 2x squared plus 4. Take the derivative, we get 2x minus 4x equal to 0. So again, x is just 0. And we get a new point, possibility 0, 1, and a blank. So far, let's see how many possibilities we have. We have 1, 2, 3, 4, and 5. But now we got the hard part, because now we also remember, we got the critical points, we checked the edges, now we have to check the corners. And this is the hard part, because the corners aren't included. If we go back up to our graph right here, the corners aren't included in our derivatives because the slope doesn't exist there. That's like our edges from last year, or endpoints from last year. The derivative doesn't count, we can't find the derivative at a corner or at an edge. So we have to check them manually. But this one's not so bad because we kind of have it with our bounds. The first one is going to be -1, -1, -1, -1, 1, 1, and 1, -1. I just looked at my corners. It's just the corners are just from my bounds. 1, -1, 1, -1, right there. All right, so once we have them, so now let's count how many we have. There's a lot here. Okay, let's see here, we count them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have to check 9 points. So I'm going to do this on a separate sheet right here. Hold on here. There we go. So let me go and list them out. So now we're going to do our candidates test. This is just like last year. You're going to make a table, but this time it's going to be our point xy, and over here our function f of xy. So our first points that we have, we pick 0, 0. We got -1, 1/4. We got 1 and 1/4. We got 0, 1, 0, -1, -1, 1, 1, 1, 1, -1. Oops, I think I forgot one. -1, -1. There we go. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're going to plug them into our function, which was this x squared plus 4y squared minus 2x squared y plus 4. And we just plug them all in. I'm going to do this for you. Here we get 4, 4.75, 4.75, 8, 8, 7, -1, 1 was 7, 1, -1 is 11, and -1, -1 is also 11. Whew, there we go. I just typed them all in for you. And now we just have to pick, well, which is the largest value? Where's my absolute minimum? Well, it's going to be the smallest value, 0, 0, 4. There's our absolute minimum. Where's the absolute minimum? Well, we have 2 of them. You can have more than one. There's our absolute maximum. And there we have it. That is our candidates test in multivariable calculus. And let's see if it kind of matches up here. And yeah, it does kind of match up. There's 0, 0, 4. and you can check the other values as well. All right. Hope you enjoyed this wonderful video. Please come by for the second one, okay? See you soon. Hold on.